In the last few lectures, if you recall, we had discussed the various types of latches and flip flops, how they work. We talked about both edge triggered and the master slave variations of flip flops, which are very useful in designing synchronous sequential circuits. But there are some timing issues which we have not discussed so far. For instance, what should the clock frequency be? What is the maximum frequency with which a circuit can operate without any errors, and so on and so forth. So, we shall try to address some of these issues in this lecture. So, the title of this lecture is clocking and timing. Fine. Let us first try to understand why timing issues are important in a synchronous sequential circuit. Now, let me repeat, a sequential circuit is said to be synchronous if there is a clock frequency and all state changes and outputs are generated in synchronism with the clock. So, synchronous sequential circuit means that there is a clock which is fed to the flip flops, and the flip flops would be working, would be changing the states in synchronism with the clock edges. Okay. Now, as I had said, there are several timing issues that need to be considered that we shall be seeing. Now, these timing issues relate to some properties of the flip flops. For example, given a flip flop, when the clock edge arrives, the question is when should we apply the data inputs? Consider a D flip flop, some value should be applied to D and then the clock pulse should be applied, the clock edge should come. Now, minimum what is the time duration before which the data should arrive, and only then the clock edge can come. Those timing constraints should be considered, and also after the clock edge come, how much more time I should hold my input data steady, so that the data can go inside the latch without any problem. These are some issues which relate to the properties of flip flops, how fast they are and so on. And of course, there are some issues which relate to the delays of the circuits which are outside the flip flops. So, we shall be considering all of these taken together will determine the maximum speed of operation of the circuit, and we normally designate the maximum speed of operation in terms of the clock frequency, right. So, let us now look at some basic definitions with which we can explain these issues of timing in a much better way. The first definition we talk about is clock width. Clock width says, suppose this is my clock pulse. Now, I can even give the clock pulse like this, a very narrow pulse. Now, this clock width constraint says that what must be the minimum time duration for which the clock signal should be high, it is this duration, this time is T w, right. So, there is a minimum duration of the clock pulse width which should be there in order the flip flop works properly. This is the clock width constraint. Then we have something very important, this is called setup time. Setup time I shall be giving some examples later, but let us look at the definition. We designate the setup time by T setup. This is defined as the amount of time the input to a flip flop. Input to a flip flop means it can be a D input for a D flip flop, it can be S and R input for an SR flip flop, J and K for a JK flip flop and so on. the time the inputs of a flip flop must be applied and must be held stable before the clock transition comes. Like if I look into the axis of time, suppose this is the time where all the inputs are stable and this is the time where my clock edge comes. Let us say for a positive edge triggered, my clock edge comes here. So, this is the duration for which my data remains stable before the clock edge, that is defined as the setup time, and setup time is a characteristics of the flip flop that you are using. Depending on the flip flop that you use, it has a specified setup time and the input must be applied at least before that amount of time. So, in a similar way, you have another timing constraint called the hold time, denoted by T hold. This is on the other side of the clock edge. This is the amount of time the input of the flip flop must be stable after the clock edge comes. That means, for a positive edge trigger the clock goes high, or a negative edge trigger clock goes low. So, again in the axis of time, if I say that my clock, let us say positive edge triggered, my clock comes here at this point in time. So, what is the minimum duration I must hold my input stable after this? Let us say this much, and this duration is my T hold, my hold time. So, setup time specifies with respect to clock edge how much before I must apply the inputs, and hold time specifies again with respect to the clock edge how much more I must maintain that input stable, so that the flip flop works correctly. Okay. And of course, there is another delay to be considered, it is the propagation delay. So, you see these are the constraints we talked about, setup time, hold time, but the flip flop as a circuit, it will be having its own delay. There are so many gates, all the gates will be having some delay. So, what is the minimum time after the clock edge has come that the output will start to change? That is the propagation delay of my whole circuit, in this case the flip flop, right. So, the propagation delay we can define in two ways, propagation low to high transition and propagation high to low transition. So, after the clock has appeared, this signal, output signal, it can be, it was low, it becomes high, or it was high, it becomes low. So, what is the total delay? Okay. Suppose the clock came here, this is the clock. So, with respect to the clock, what is the delay after which the output starts changing, that is denoted as T propagation delay, low to high or high to low, as the case may be, right. Let us take an example. Consider a scenario like this. Here we have a simple D flip flop with a D input and a clock. So, in the clock input I am applying a clock pulse like this. So, I am showing only one single clock pulse. Suppose this is positive edge triggered as the symbol shows. So, the circuit will be triggered by the positive edge of the clock, that means this edge. Now, in this case is the input data, which is only a single data D. The input data is coming. So, what I am saying is that before the clock edge comes, my input data must remain stable for at least a time equal to T setup. This is my setup time. And after the clock edge has come, I must maintain the data stable for another duration of time. This is my hold time, T hold. So, if you maintain this T setup and T hold constraints, then your flip flop will be working correctly. Otherwise, if you apply the inputs too late or remove it too early, the data that will finally get stored in the flip flop may be wrong. So, you need to satisfy the setup and hold constraints in a flip flop like this as I have shown. Let us take another diagram to show this part. The other delays are also shown here. So, here again we have a D flip flop with a D input, a clock input and output Q. I am not showing Q bar, I am only showing Q. So, let us assume that in the clock input I am applying a clock pulse, and because this is positive edge triggered, it will be triggered in the positive edge of the pulse. This is my triggering edge. Now, suppose in my D input I am applying some signal like this. See, when this clock edge comes, the value of D is 1, this point. So, this T setup is the minimum duration before this edge. I must apply this D equal to 1 and leave it like that. Similarly, after the clock edge comes, this hold time T hold, I must maintain D for this much time again. And after the clock edge comes, let us say here this red vertical bar, how much time it will take for the output to change. This is my propagation delay. Now, since here D was 0, it is becoming 1. So, Q will also become 1. So, this is a low to high transition. So, this is denoted by propagation delay low to high. This is here, and suppose later again when the next clock comes, my D is 0, here the value of D is 0 here. So, again I must apply this 0 T setup time before and maintain it for a duration of T hold after this. Now, the output, since it goes from 1 to 0, now the corresponding delay will be T p high to low. Now, for a flip flop, typically these two delays are equal, but in case they are unequal, that is why we use two different symbols LH and HL. So, in this diagram we show all the relevant delays, and of course, the width of the clock pulse, that is T W I mentioned, that is also shown. Now, the next question is, when we connect more than one flip flops, one after the other, we say that it is a cascade of flip flops. What will happen? Let us look at a very simple scenario where two flip flops, two D flip flops, the simplest kind of flip flop, are connected in cascade. So, input signal in is applied here. The first flip flop generates an output Q 0, which is fed as the input to the next flip flop, and this Q 1 is the final output, and the clock signal is applied to both the clock. Let us assume these are both positive edge triggered. Now, there are some considerations you need to look here. Like the first thing that we are saying is that, what if the flip flop propagation delay exceeds the hold time? Well, what do you mean by it? Let us look at the clock signal. Suppose the clock signal was coming like this. This was the active edge of the clock. Just assume that hold time and setup time constraints are being satisfied. So, after some propagation delay, so I am showing it after the clock edge comes, the output Q 0 will be available. This is equal to the propagation delay T p, well, either low to high or high to low. Okay. So, it is at this point that the output Q 0 is available, okay, after the delay of the flip flop. Now, what I am saying is that, what if the flip flop propagation delay, this T p L h, exceeds the hold time? Because you see, when the clock signal comes like this, the same clock signal is applied to both the flip flops. Consider the second flip flop, the second clock pulse has come. Now, the value of q 0, this q 0 should be held stable at least t setup time before the clock edge comes. Now, if this t PLH is too large, so that it eats up into this t setup time, then the setup time constraint would be violated. This can be a problem. Okay. So, you should be careful enough that the clock frequency should not be too fast that such a thing happens. Now, let us show a scenario. This is the correct scenario, where all the timing constraints are met. Let us see, this is my clock signal, this is my first edge, this is my second edge. So, I am applying some value input here. So, when the clock edge comes, it is here. So, I have applied the input at least t setup time before that, and the input is stable till t hold, this is fine, and output q 0 will be available after the clock pulse after a delay of t propagation low to high, because q 0 is changing from low to high. Considering the second flip flop will be taking this q 0 and input and store it there. So, this input, this new value of q 0 at the next clock, this next clock will be coming to the D input of the second flip flop. So, for the second flip flop, again you see the setup time constraint is satisfied, because the q 0 is available here only. So, it is much buffer to sufficient buffer is here, and of course, hold is also there. So, after that time q 1 will go from low to high. So, it is T P H L this, after this delay this q 0 1 value will get stored here, right. So, this shows the basic requirement of the timing constraint, which you see once more carefully. You see, this is your total time period of the clock, starting from here, the first stage up to the next stage. Now, within the time period, what are the things that are included? You must have one setup time, you must have this propagation delay, and of course, hold time and propagation delay can overlap. So, setup time and this propagation delay are the most important delays that must be included here. So, when you talk about edge triggered clocking, well, this edge triggered may be either positive edge triggered or negative edge triggered, both ways. So, to summarize, data that is generated from the output of the flip flop, let us say at time t, must arrive at the next flip flop one setup time before t plus capital T, where t is the clock period. This is exactly what I mentioned in the previous diagram. It must appear one setup time before this, and the second thing is that the delay from each input flip flop to each output flip flop of a combinational block should be less than t minus setup. So, if the flip flop is too slow, then it will be eating up into the setup time of the next flip flop, and the timing violation will result. There is another issue which we shall be talking about very briefly later, that the clock signal does not arrive exactly at the same time to all the flip flops. There will be some delay, because when the wires are laid out on a chip, when a chip is fabricated, there can be the flip flops which are spread all around the chip. The clock is generated at some point and it is connected to all the clock inputs of the flip flop. Now, the delays of these wires, because the wires may be of unequal length, their delays will also be unequal, not the same. So, if you are not careful about this fact, then the clock edge might reach the flip flops slightly varying in time, either a little early or a little late. So, if you are not careful, this may lead to incorrect behavior of the circuit. Okay. This is called clock skew. This is referred to as clock skew. But here we are not discussing in detail regarding clock skew. Let us now look at a couple of examples. Let us see how these flip flops that we have designed, we saw how it can be designed, how they work, how they can be used to carry out certain very useful things. The first example we considered here is one of frequency division. What do you mean by frequency division? We are saying that suppose we have, I already have a clock signal of f hertz. What is hertz? F number of oscillations per second, that is the definition of hertz. So, we want to divide this frequency by 2, we want to generate another clock signal, let us say, whose frequency will be f by 2. So, how do you do it? Let us say I have a frequency of 1 kilohertz or let us say 2 kilohertz, and I require means another let us say clock of frequency 1 kilohertz, half of that. So, this is extremely easy to do using a special kind of a flip flop. Let us take a T flip flop, T flip flop with the output, and let us say this is my clock. So, what I do, let us apply a constant 1 on the T input, and in the clock input I apply that f hertz clock frequency. So, what I claim is that at the output whatever will be generated, that will be a f by 2 hertz clock signal. Well, how does it happen? Let us look into it with respect to a timing diagram. So, I am showing a clock pulse, I am showing 4 pulses. So, this is coming continuously. Now, you think of a T flip flop, this is a positive edge triggered. So, this is the active edge, 0 to 1 going, this is the active edge of the clock. Now, what will be the value in q? Suppose initially the value of q was 0, let us say. Because t is 1, what is a T flip flop? A T flip flop says that if the T input is 1 and a clock comes, the output will toggle. If it was 0, it will become 1, if it was 1, it will become 0. Here I am applying T continuously as 1. So, every time a clock comes, the output will toggle, right, because T is always 1. So, whenever the first clock comes here, let us say this Q will toggle, this will become 1. The next clock comes here, it will again toggle, it will become 0. Next clock is here, it will again become 1. Next clock is here, it will again become 0. So, you see for the original clock, let us say over this time duration which I have drawn, there were 4 pulses that were generated. Here for every 2 pulses, 1 pulse is generated, only 2, which means I have reduced the frequency by half to half. So, a simple T flip flop like this can be used to divide the frequency by 2. Now, means another advantage is there, if you want this, that in the output of Q, the clock, the on period of the clock and the off period of the clock, if you call them T on and T off, they will be exactly equal, and they will be equal to the time period of the original clock signal. If this was your time period, both T on and T off will be equal to the time period. So, I will be getting an exactly square wave with equal on and off durations, right. So, this is one example. Let us extend this example further. So, here what I am saying is that again we are given a clock of frequency f. So, again we are doing frequency division, but we are not dividing by 2, rather we are dividing it by some arbitrary power of 2, let us say 2 to the power k, where k is some integer, right. Let us take an example again here. Let us assume k is 3, which means I am trying to divide a frequency by 8, 2 to the power 3 is 8. So, the required circuit here will be very simple. Well, again we are using T flip flops, but not 1, but k number of T flip flops. It means 3 T flip flops. And all the T inputs I am setting to 1, just like before, and the clock, these are the clock inputs. So, the clock input of frequency f I am feeding here, the output q of the first T flip flop I am feeding in the clock of here, and output of this I am feeding here, and this is my final output. So, what I claim that if my clock input frequency is f, then here the frequency will be f by 8. Okay, let us call this q 1, q 2 and q 3. Let us work out how it works. Suppose I have a clock pulse here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let us say 10 pulses, and this is the active edge, right, leading edge triggered, this is the active edge of the clock. So, if you plot q 1, so q 1 will toggle every time the active edge of f comes, because t is 1 with respect to the c k. So, q 1, suppose initially it was 0. So, it will toggle once here, again here, again here, like this it will go on toggling, right, like this. So, the clock frequency was f, for q 1 it will be f by 2, just as we discussed earlier in the previous example. Now, think of q 2. For q 2 the clock input is q 1, q 1 is fed to the clock. So, same thing will happen, but with respect to the active edge of q 1. So, if q 2 was also 0, so first toggling will be here, next toggling will be here, next here, next here, next here, and so on. So, you see for every 2 pulses of q 1, 1 pulse of q 2 is generated. So, the frequency here will be f by 4, and again q 3, for q 3 this q 2 is fed as the clock of the last one. So, similarly, if this is also 0 initially, there will be 1 toggling here, 1 toggling here, 1 toggling here, and so on. So, for 2 pulses of q 2, 1 pulse of q 3 is generated. So, this will be f by 8. So, you see just by using a chain of T flip flops, we can very easily divide an input clock frequency by any arbitrary power of 2. So, these are very interesting features of a flip flop, of a T flip flop in particular, that is very useful whenever we want to generate some specific, you can say, timing signals with some frequency relationships with respect to an original signal. Okay. So, with this we come to the end of this lecture, where we had discussed some of the timing and clocking issues that pertain to circuits when you use flip flops. and we shall be continuing our discussion in the next lecture as well. Thank you.